Alrighty, we have been talking about chemical and physical properties of matter along with signs, the five main signs of a chemical change. Now we're going to take a time out and just spend a little bit of time talking about how everything that goes into a chemical reaction must come out of a chemical reaction. Remember that when chemicals react, the types of atoms that go in, like for example, if you look at this chemical reaction listed on this worksheet, nitrogen and fluorine, are the same as the chemicals that come out, nitrogen and fluorine. But what's connected to what makes all the difference in the world in the properties of those chemicals and how they behave. So if you recall, we talked about before sodium and chlorine reacting to form sodium chloride. And we said that sodium is a very dangerous metal, and it is highly reactive and can even catch on fire with water. We also talked about how chlorine is a poisonous gas, and if you were to breathe it in, it could kill you. But when we react these two chemicals together and they form a new compound, sodium chloride or salt, the properties completely change, and salt is something that we can eat. So during a chemical reaction, the types of atoms that go in are the types of atoms that come out, and the numbers of atoms that go in, one sodium, one chlorine, are the numbers of atoms that come out, so one sodium, one chlorine, but the properties of the chemicals totally change. Today, we're going to focus a little bit more on conservation of mass, which tells us that the number of atoms that go in equals the number of atoms that come out. So the law of conservation of mass tells us that the total amount of matter is neither created nor destroyed during any physical or chemical change. Therefore, the mass stays the same before and after a chemical reaction. So if we were to run a reaction on a triple beam balance, and we did it inside of let's say a Ziploc bag, a closed baggie, so that if a gas was produced, it couldn't escape, we would find that the mass of the reactants, what we were putting in, would equal the mass of the products. If we allowed the reaction to go forward, the chemicals to mix, a new product to be made, the mass of that product would weigh exactly what the mass of the reactants were. So chemical equations demonstrate this principle because they're always what we call balanced. The total mass of the reactants must equal the total mass of the products. You can check to see if an equation is balanced by counting up the number of atoms it has to be the same on both sides of the equation. So if you look at this equation again, we see that 2 nitrogen are going in, 2 are coming out. 6 fluorine going in, 2 times 3 is 6 fluorine coming out. When we balance a chemical equation, it's okay to change the coefficients or these numbers in front of the chemical. It's never okay to change the tiny little numbers to the right of a chemical symbol, because if you do that, then you're changing the type of chemical that you have. So, for example, if we were doing a reaction, which we are here, where we're reacting hydrogen gas and oxygen gas to form water, it would be okay to put a big 2 in front of our water, and that just signifies that we have 2 water molecules. It would never be okay to try and put a number 2 after the oxygen, because that changes the chemical that we have. So this is water, this is hydrogen peroxide. So it's never okay to change the little number to the right of a chemical symbol, because that'll give us a different chemical. So when we're balancing equations to uphold the law of the conservation of mass, we need to first count the number of atoms that we have going in and coming out. So if you look at this chemical equation, that represents a chemical reaction, again, of hydrogen and oxygen gas forming water. We want to show that the number of atoms in the reactants equals the number of atoms in the products. So we're going to count up and see if this is balanced. We've got 2 hydrogen going in, and we've got 2 hydrogen coming out. We've got 2 oxygen going in, and we only have one oxygen coming out. So we've got a problem here. This is not truly the way this reaction is happening. It does not uphold the law of conservation of mass. So we have to try and balance this chemical equation. Now, when I balance, and you should always do this in pencil because you can make a lot of mistakes with this, but when I balance, I always try to start with an odd number. It doesn't always work, but oftentimes it does, and I try to do what I can to make it even. So I've got one oxygen atom here. I'm going to put a big 2 in front of here. And of course, remember that just means we have H2O 2 times. Okay, so now I've got 2 oxygen atoms coming out, and look at that. I have 2 oxygen atoms going in. So I've balanced my oxygen. But in the course of doing that, I've thrown off my hydrogen. So now I have 2 plus 2 is 4, or 2 times 2 is 4. 4 hydrogens coming out, but I've only got 2 going in. So I'm going to put a big 2 in front of this. And now I've balanced my equation. And this tells me that it requires 2 molecules of hydrogen gas to react with 1 molecule of oxygen gas, producing 2 molecules of water. And this is upholding the law of conservation of mass because the numbers and types of atoms going in is equal to the numbers and types of atoms coming out. Okay, so let's try another one. And in this one, again, this is our reactants on the left. This is our products. And we want to accurately represent what's going on in the chemical reaction. So we have 4 phosphorus going in, 2 coming out. So again, there's a problem. That's not really what's happening. And we have 2 oxygen going in and 3 coming out. Now, again, here's that odd number. So I'm going to look at my 2 and 3 for oxygen and try to find my least common multiple. There's a math term for you. That's the smallest number that both of these numbers go into. And they both go into 6. So I'm going to go ahead and put a 2 in front of this compound. And now I've got 2 times 2 is 4 phosphorus coming out. 2 times 3 is 6 oxygen coming out. My phosphorus is balanced because I've got 4 phosphorus going in. Now to balance my oxygen, I've got 6 coming out. I could multiply this by a 3. So now I've got 6 oxygen going in and 6 coming out. So notice again that when we balance equations, we can manipulate this coefficient, which tells us the number of atoms or molecules that we have, but we can never mess with that little subscript, which is part of our chemical formula. Now, if you want to practice balancing a chemical equation to show how you understand the law of conservation of mass, showing that everything that goes in is equal to everything that goes out, it'd be a good time to pause your video and try to run through example problems 3, 4, and then on the back side, 5 and 6, okay? And I have that uploaded onto Google Classroom for you. So again, a good time to pause the video and try it, and then unpause the video and watch to see if you did it correctly. So I have 2 hydrogens or nitrogens going in, 1 coming out, 2 hydrogens going in, and 3 hydrogens coming out. It's not balanced. I see that odd number. I'm going to do the least common multiple, multiply that, and get 6 hydrogens. Okay, because remember, 2NH3 just means NH3 2 times. So I've got 2 times 3 is 6 hydrogens, or 3 plus 3 is 6 hydrogens. And now I'm going to put the 3 in front of this, and that's going to give me 6 hydrogen going in. And again, that 3H2 just means H2 3 times. Okay, so 2, 4, 6 hydrogens. Now I've got 2 nitrogens coming out and 2 going in. So this is completely balanced. Okay, now number 4, let's try this one. Okay, we've got 1 potassium going in, 1 potassium coming out, 2 chlorine in, 1 coming out. So here's our problem. So I'm going to go ahead and put a 2 in front of this, and that's going to give me 2 potassium coming out and 2 chlorine coming out. I've got 2 chlorine going in And I've only got 1 potassium, so I'm going to put a big 2 in front of that. And that will allow me to have my equation balanced. Okay? All right, now let's try our last couple problems here. They look kind of scary, but they're actually pretty easy to balance. Excuse me, we've got 1 carbon going in, 1 coming out. And we've got 4 fluorine going in and 2 coming out. 2 bromium going in and 4 coming out. So we need to balance this. We've got a couple issues here that are not balanced. So you could start anywhere, especially if you have a pencil with an eraser. It's okay to make mistakes, but I'm going to go ahead and try to balance maybe my fluorine first. And I'm going to put a 2 here. So now I have 4 fluorine coming out and 4 fluorine going in. Now I'm going to try and balance my bromine. I've got 4 bromine coming out, and I'm going to put a 2 in front of this. And that'll give me 4 bromine going in, and then I've got 1 carbon. I've got 1 carbon going in and 1 carbon coming out. So I've got it all balanced. Okay. Now our last one, we've got 1 gallium going in, 1 coming out, 3 fluorine going in, 1 coming out, 1 cesium going in, 1 cesium coming out. So here's our issue. So this time I don't think I'm going to try and get rid of my odd number because I've just got to fix that fluorine. So if I've got a 3 there, I'm going to go ahead and put a 3 here. So now I've got 3 fluorine coming in and 3 coming out. I've got 3 cesium coming out now, and so I better put a 3 in front of this. Okay, and then I've got the 1 gallium, and I've got the 1 gallium. So again, that's balanced. And the whole purpose of balancing those chemical equations is to show the numbers of atoms going in equals the numbers of atoms coming out. And that's what is truly happening during a chemical reaction.